Well, hi and welcome to this video on using simultaneous equations for chemical analysis. So in this video we're going to very quickly review simultaneous equations and then look at their applications for both Uv-Vis analysis and for gravimetric analysis. So simultaneous equations are based on intersecting straight lines. They solve the point of intersection. So here we have a line y is equal to 7x plus 3. This means it has a slope 7 and an intercept 3. We have another line y is equal to 3x plus 5. This has an intercept of 5 and a slope of 3. The point of intersection is solved by using simultaneous equations. In other words, if we take both equations again, it's usual to rewrite them so that the x's and y's are on the left hand side and the numbers are on the right hand side. We can then very simply subtract equation 2 from equation 1. That will remove the y terms and we're left with 4x is 2 and a solution for x, 0.5. We can now put that value for x into one of the equations and solve y. Okay, so here this diagram now is representing the point of intersection of the two lines. X is 0.5 and y is 6.5. So the key thing about simultaneous equations is that we have two unknowns, the value of x and the value of y, and we use two known pieces of information, the two equations of the straight lines, to find out these two unknowns. So we have two unknowns and we have two knowns. So we can take this principle and apply it to chemical analysis. So the first example is Uv-Vis absorption spectroscopy. Suppose we have an absorption spectrum of a pure compound A. So here we see that we're measuring the absorbance at 300 nanometers and at 500 nanometers. And the extinction coefficient, in other words how well these compounds absorb at these wavelengths, can be calculated from the Beer-Lambert law. A is equal to epsilon Cl, where L is the path length, C is the concentration, and epsilon is the extinction coefficient. So we can get the absorption at 300 and the absorption at 500 and calculate the extinction coefficients. We can do exactly the same for compound B, another compound. Again, we can get the extinction coefficient for B at these two wavelengths using the Beer-Lambert law. If we now have a mixture of these compounds, or we don't know the concentration of each of the components in the mixture, all we can measure now is the absorption at 300 and the absorption at 500. We can't get the concentrations because we don't know the extinction coefficients because it's a mixture. We don't know how much there are of each compound. What we can say is that the absorption at 300 is equal to the absorption at 300 for A plus B, and the absorption at 500 is equal to the absorption for A and B at 500. So we have two unknowns, the concentration of A and B, and we have two pieces of information, the absorption at 300 and the absorption at 500. So here's an example where we measure the absorption at 300 and 500 to be 0.35 and 0.23. We know the extinction coefficients of the pure compounds at these wavelengths, and we can now calculate the mixture, the concentration of A and B in the mixture. So again we said that we know that the absorption at 300 is equal to the absorption of A at 300, so I'm putting in the Beer-Lambert term there, and the absorption at B at 300, and similarly for 500. L, the path length, is going to be 1 centimeter, and I'm just going to rewrite the equation so that the concentration of A is X and the concentration of B is Y. So I can rewrite this equation now. So it says that the absorption at 300 is 0.35. So just putting in the numbers, epsilon times A, so that's 80 X plus 150Y. And then the absorption at 500 is 52X, that's the extinction coefficient at 500 for A, plus 100Y, the extinction coefficient at 500 for B. If I multiply my second equation by 1.5, that will match up the Y values. So now if I subtract the second line, the second equation from the first, I'll be left with an expression for x. So this gives me 2x is equal to 0.005. So x is equal to 2.5 by 10 to the minus 3 molar. It's molar because, remember, this is a concentration. I can put my number back into one of those equations and get a value for y. Let's look at another example now where we use it in gravimetric analysis. Suppose we have a mixture of two salts, sodium chloride and potassium chloride, and all we know is the total mass of that mixture. This is precipitated out with silver ions to give 5.13 grams of silver chloride. So we know in this question, we know the mass, the total mass of sodium chloride and potassium chloride. We know the mass of silver chloride. And we can see that the total amount of chloride on the left-hand side is equal to the total amount of chloride on the right-hand side. So we have two unknowns, the mass of sodium chloride and potassium chloride, and we have two pieces of information, the total mass and the fraction of chloride on each side. To use the fraction of chloride on each side, we can say that the proportion of chloride in x grams of sodium chloride is the atomic mass of chlorine divided by the total molecular mass of sodium chloride times its mass, so that's 0.61x. The same for potassium chloride, except here I put in 39.1 because that's the atomic mass of potassium. That gives me 0.48y. And the same for silver chloride, except now I know the mass of silver chloride, so I can put that in. So that gives me 1.27 grams. So I can build up the second equation now to say that the mass of the fraction of chloride in sodium chloride plus the fraction of chloride in potassium chloride is equal to the fraction of chloride in silver chloride, 1.27 grams. So my first equation was the mass of sodium chloride plus the mass of potassium chloride is 2.3 grams. I incorporate my second equation, just derived. If I now divide my second equation by 0.61, that matches up the x values and allows me to calculate a value for y. I can then plug that number back in to get a value for x. So my mass of sodium chloride was 1.36 grams, and my mass of potassium chloride is 0.94 grams.